All right. 6.2 is an extremely long section, and this is the very last topic and the very last example. So we made it. Average value. So we can talk about, well, we are used to talking about the average of lots of different things. Average height, average weight, average test score, all things that we're very familiar with and that we've calculated hundreds of times, if not thousands of times. So let's just remind ourselves, if you've got a finite list of values, so you've got a list of values, maybe they are test scores. Person 1's test score, person 2's test score, all the way through the last person's test score. We know that to calculate the average, we just add these values all up and we divide by the number of values that we summed. Or, written in summation notation that you should be familiar with from Calc 1, this is shorthand. Let's just do a quick review here in case you are not. This is saying things are going to be labeled or indexed by the letter I. So this represents the ith test score. And then we are going to add them all up until we get to n. So this numerator is just mathematical shorthand using summation notation, and that expands to this. So this is an abbreviation for this. Okay, so this is how you would calculate the average test value, or the average weight, the average of this set of values. Okay, well, is it possible, does it even make sense to try to figure out or define the average value of a function? So unlike this list of values, there's a finite number of these. Whereas a function, if I go ahead and have a graph of some function, and let's say we're only looking between x equals a and x equals b, so we're only interested between here and here, we want to know what is the average of all of these values. In other words, all of these y values, every y value here. Okay. Well, how many y values are there from there to there? Although this distance is not infinitely long, there are an infinite number of values there. So this would somehow be a sum of infinitely many values that vary continuously. So how would we go about doing that? Okay, so what we could do is our usual approach or technique in Calc 2 and in Calc 1 towards the end when we first started talking about integration is, if you have that function from a to b, you can imagine splitting this up into lots of little pieces. So a becomes x0, b becomes xn, so we split this up into n little values, x1, x2, so on and so forth. Here we have x sub n minus 1, so on and so forth. And then if we highlight, let's say, this range right here, this would be, let's say, x sub I, and the previous would be x sub I minus 1. So really what we're doing is we're just adding these values up. Not the x values, but the y values. So if we think about this, we want to figure out what this y value is. Well, y sub I is the same thing as f of x sub I. So that's exactly where this numerator comes from. We split this, we approximate the average value of the function by figuring out the value of the function at a finite number of points, figure out the value of f at all of these points, and then take that average over n points. And then we keep doing it for more and more points. So we could then go through and subdivide this in again and get double the points and keep doing that. So if we do that, this is what it looks like. And if we throw a limit on here as n goes to infinity, we're trying to work towards this idea of a Riemann sum. And then this little step right here is a fairly common thing in math, where if you want something but you don't have it, you try your best to get it by doing something legal. In this case, multiplying by the number 1. You can multiply anything by the number 1 and it stays the same. So we just choose to multiply by a fancy form of the number 1, which is this guy. Why would we choose to multiply by this particular fancy form of the number 1? Well, it's because b minus a over n is delta x. That is the separation. That is the width here. Delta x is b minus a over n. So, since we notice we have a 1 over n in our problem, we could multiply by b minus a over b minus a, and then this grouped together becomes our delta x. Then the remaining 1 over b minus a is a constant, so it can be pulled out. And then what remains is the definition of the integral. This right here is a Riemann sum, and the limit of a Riemann sum is this integral. So this would be the average value of f. So specifically, I want to add in here, just to be very specific, it is the average value of f for x between a and b. Okay. Something else that's important too, conceptually and geometrically, is if you were to actually calculate this average value for a given function, then this would equal some number, and this number would be the average height of the graph. It's also sometimes called the mean value of f. Okay? So, in particular, it's interesting to note that, let's say here's my function f between a and b. Now the average value of the function is probably, I don't know, if I had to guess, I'd probably say the average y value between here and here. This is almost a line, so it almost varies linearly, in which case, if it varies linearly, I would assume that the average value would be the very middle value, so like right about here. So I would assume that this is the average value. So let's go ahead and mark that down and say that's the average value. In which case, if you considered this function, so let's say this is y equals, I'll say mu for the average value. So mu here is the average value on a to b. What's interesting to note is that the area under this curve, right here, this area in red is exactly the same as the area under the blue. It's exactly the same. Okay. So, for example 9, let's actually determine one of these. Determine the average value of this function, secant squared, on the interval pi over 6 to pi over 3. So from 30 to 60 degrees. So, first of all, I would set this up. So 1 over pi over 3 minus pi over 6. The integral from pi over 6 to pi over 3. And then here our function is secant squared, x dx. This is a little bit annoying, but you can figure this out pretty easily. First, we'll just get a common denominator here, which is 6. So 2 pi over 6 minus pi over 6 is pi over 6. All right, yep. So if we're dividing by pi over 6, that's multiplication by the reciprocal. So I can rewrite this as 1 over pi over 6, or 6 over pi. And then the antiderivative of secant squared is tangent, since the derivative of tangent is secant squared. Okay? So 6 over pi, and then, of course, tangent of pi over 6, well, that's going to be the sine of pi over 6, which is a half, divided by the cosine of pi over 6, which is root 3 over 2. So this is 1/2 times 2 over root 3. So 1 over root 3. And then minus the tangent of pi over 3, which is just going to be the reciprocal of this, since sine and cosine values are flipped. They are opposite for pi over 3 and pi over 6. So this would be root 3 over 1, or just root 3. And I won't bother getting or making this look any nicer than it is. That's good enough. So that would be the average value.